Good morning, students. In this section, we are going to deal with the AC flowing through a series LCR circuit. That means what happens when AC flows through an inductor, a capacitor and a resistor which is connected in series. So I will explain this with the help of a phasor diagram. So before that, let us see some points. We already know EMF equal to E0 sin omega t. Now, in resistor, we already know current and voltage are in the same phase. That is the first point. In resistor, current and voltage are in the same phase. In inductor, second point. In inductor, the current lags behind voltage by pi by 2. Third point, in capacitor, the current leads the voltage by an angle pi by 2. So I take these 3 points into consideration and then I will draw the phasor diagram. Using phasor diagram, we will derive the expressions. Okay. So let us see how to draw the phasor. I first draw the x-axis and y-axis, and in resistor current and voltage are in the same phase. So I will write, I will do voltage like this and I will do current like this. Current and voltage are in the same phase. So this is I0, this is V0. I'll do one thing. It is always better to draw the current magnitude lesser than the voltage magnitude, because whenever current flows through the circuit, the magnitude of voltage will be always greater than that of the magnitude of the current. Therefore, we will draw the current first and voltage second. Okay. So this is current, and then this will be the voltage. So voltage across the current, voltage across the resistor and the current across the resistor, both of them are in phase. So I will mark here omega t, and this is I0 and this is VR, voltage across the resistor, VR. Now consider the case of inductor. As I told, in inductor voltage lags, current lags. In inductor the current lags, that means the voltage is leading. So for inductor I will draw VL like this, voltage is leading. So I will draw VL like this. I write VL. Now in capacitor current is leading, that means voltage is lagging. So for capacitor I will draw the arrow like this. This will be VC. Purposefully I have drawn VC lesser than VL. I can do it the other way around also, VL less than VC, but in this case I am discussing when VL is greater than VC. And you can see that VL and VC are 180 degree out of phase. One is towards that quadrant, one is towards the fourth quadrant. They are 180 degree out of phase. So I can subtract VL minus VC. So VL minus VC will be somewhere here. I put an arrow and I write here VL minus VC. Now you have seen, you have two things. The first vector is VL minus VC and the second vector is VR. So I am going to form the parallelogram connecting both. So let us draw the parallelogram. I have drawn the parallelogram, and using that parallelogram, the diagonal of the parallelogram gives the resultant. So I am going to draw the diagonal from here. This is the diagonal. This diagonal will give the resultant vector. So the resultant voltage V is marked here. So from this phasor diagram, it is clear that current is here and voltage is leading the current by an angle phi. Or we can say the current is lagging the voltage by an angle phi. So in the graph, how I mark is, I will mark this full angle. Just wait a minute. This angle I mark as omega t, and this angle I mark it as phi. Okay, so I can say omega t, V is equal to V0 sin omega t, and I is equal to I0 sin omega t minus phi. I is equal to I0 sin omega t minus phi. So from here it is clear that the current is lagging by an angle phi. Now what would happen if I do VL? What would happen if I do VL less than VC? Then the graph will be like this. VC minus VL will come on this quadrant. So the resultant voltage, this resultant voltage would come in this quadrant. That means if VC greater than VL, the current will be leading by an angle phi. Okay, I repeat once more. In this graph, it was VL greater than VC. So current lags by an angle phi. If VC greater than VL, then the current would lead by an angle phi. So from here, I can derive the expression for the total voltage, the total resultant voltage. So the resultant voltage can be given by V is equal to root of VR square plus VL minus VC the whole square. Because V is the hypotenuse, this is the base, this is the altitude. This altitude is VL minus VC. So VR square plus VL minus VC the whole square. So V is equal to, what is VR? VR can be written as I into resistance, current into resistance whole square. VL can be written as I into XL, and VC can be written as I into XC whole square. Okay, now I can take I square common from everywhere and take it outside the root. So it becomes I. So the next step is V is equal to I into root of R square plus XL minus XC whole square. XL minus XC whole square. And in the next step, I do V is equal to V by I. V by I is equal to root of R square plus XL minus XC whole square. Now, what is V by I? You will say R immediately. But here, it is not only R. There is inductor, there is capacitor, there is resistor. So V by I is a new factor which is called impedance. I write Z. V by I is equal to Z, which is called impedance. R square plus XL minus XC whole square, where Z is the impedance of the circuit. So what is meant by impedance? Impedance means it is the effective opposition caused by all the components to the flow of AC. It is the effective opposition caused by all the components, that means inductor, capacitor and resistor, to the flow of AC. That is why impedance is having this equation, R square plus XL minus XC whole square. And I can write one more thing. Z is equal to root of R square plus XL can be written as L omega. We wrote in the previous video, L omega, and XC can be written as 1 by C omega. So impedance can also have one more equation like this, root of R square plus L omega minus 1 by C omega whole square. Okay. Let us see how to find the phase angle. The phase angle tan phi is equal to XL minus XC by R, because tan phi is opposite by hypotenuse, opposite by adjacent side. So XL minus XC by R, and XL is L omega and XC is 1 by C omega. So L omega minus 1 by Z omega divided by R. Okay. And phi is called the phase angle. Now here you see I have written certain cases. The first one is case 1, when XL is greater than XC. When XL greater than XC, L omega is greater than 1 by C omega. At that time tan phi is positive. We say phi is positive. So we can say that the current lags behind the EMF by a phase angle phi, and the LCR circuit is inductance dominated circuit. That means we call by the name inductive LCR circuit. So remember that condition. If XL greater than XC, the LCR circuit is called inductive LCR circuit. Similarly, if XL is less than XC, then tan phi is negative, phi is negative. So current is leading the EMF by a phase angle phi. Then we can say that it is capacitance dominated circuit. That means at that time we will say that it is capacitive LCR circuit. Okay, it is capacitive LCR circuit. Then when XL equal to XC, L omega equal to 1 by C omega, then what will happen? Tan phi is equal to 0, phi equal to 0. Therefore we can say that current and EMF are in the same phase. That means the circuit behaves like purely resistive circuit. Circuit behaves like purely resistive circuit. And at this condition, think about the equation for impedance. Equation for impedance is root of R square plus XL minus XC whole square, right? If XL and XC are same, this is gone, no? XL minus XC is 0. So Z equal to R. That means impedance of the circuit is equal to resistance. Which means in the third case where XL equal to XC, the circuit behaves like a purely resistive circuit. And current and voltage are in the same phase. Okay. So we will say like this, when XL equal to XC, tan phi is equal to 0, which means phi is equal to 0, and as I told, z becomes r only because this one will be 0. Z becomes r and maximum current will be E by R. That is why we told impedance offered by the circuit is minimum and the current is maximum. This condition is called resonant condition. This condition is called resonant condition. And the frequency at which the resonance condition take place is called resonant frequency. So let us see what is resonant frequency. See, at the resonant condition, the angular frequency omega r, angular frequency is omega r. So I will write XL equal to XC. What is XL? L omega. What is XC? 1 by C omega. So L omega equal to 1 by C omega. From there, omega is taken to this side. So omega square is equal to 1 by LC, or omega is equal to 1 by root LC. Now omega can be written as 2 pi into F. F is frequency. Omega can be written as 2 pi into F. So here 2 pi into F is equal to 1 by root LC. Then what is F? 1 by 2 pi root LC. So this is the expression for the frequency, resonant frequency. So expression for resonant frequency is F is equal to 1 by 2 pi root LC. Now they can ask one more question regarding this case. They can ask you to draw the impedance triangle. So what is meant by impedance triangle? It is a triangle which is drawn to represent the impedance of a circuit. For example, see, from the phasor diagram we got this triangle. This triangle. I am making this triangle in the parallel way. So look what I am doing now. See, here I write impedance, and here I write XL minus XC, and here I write R. This angle is phi. This is the triangle which is called impedance triangle. It is used to find the impedance of the circuit. So using this triangle, how will I find the impedance of the circuit? Just use Pythagoras theorem. Hypotenuse is equal to root of base square plus altitude square. Now from this triangle, how will you find tan phi? Tan phi is equal to opposite by adjacent, XL minus XC by R. So phi is equal to tan inverse of XL minus XC by R. Okay, so first use of impedance triangle is find the impedance of the circuit. Second use of impedance triangle is find the phase angle between the voltage and the current, which can be immediately found by using this equation. The third use of impedance triangle is to find the power factor. Power factor is represented as cos phi. And what is meant by power factor, we will discuss in the next video. Now here power factor is represented by cos phi. From the triangle you can just see what is cos phi. Cos phi is equal to adjacent by hypotenuse. So this is the power factor. So impedance triangle have three uses. First one to find the impedance of the circuit. Second one to find the phase angle between the current and voltage. And the third one to do the power factor, to find the power factor. That's all in this section.